What are photonic qubits for quantum computers? Have you ever wondered how quantum computers process information differently from traditional computers? One fascinating aspect is the use of photonic qubits. So, what exactly are photonic qubits? Let's break it down. Photonic qubits are the basic units of quantum information that are encoded in individual particles of light known as photons. These qubits harness specific properties of photons, such as polarization, path, time-bin, or frequency, to representing and manipulate quantum states. This ability allows photons to exist in superpositions, which is a key feature that enables quantum computation. In optical quantum computing, photonic qubits play a vital role. Photons have a remarkable ability to maintain their quantum coherence for extended periods, allowing them to travel long distances with minimal interaction with their environment. This characteristic makes them highly suitable for quantum communication and distributed quantum computing networks. Unlike many other types of qubits, photonic qubits can operate at room temperature and utilize existing optical fiber infrastructure, making them easier to scale and integrate with current technologies. There are several methods to encode photonic qubits. One common approach is polarization encoding, where horizontal and vertical polarization states representing the qubits 0 and 1. Another method is path encoding, which uses two distinct optical paths, with a photon's presence in one path corresponding to 0 and in the other to 1. Time-bin encoding is another technique, where information is encoded based on whether a photon arrives early or late within a specific time window. Lastly, frequency encoding uses different photon frequencies to representing qubit states. Photonic quantum computing manipulates these qubits using optical components like beam splitters, phase shifters, and polarizing filters. However, a challenge arises because photons do not naturally interact with each other. This makes it difficult to implement two-qubit gates, which are necessary for universal quantum computation. To address this, techniques such as measurement-induced nonlinearity are employed, where additional photons and detectors create effective interactions probabilistically. There are two main approaches in photonic quantum computing. The first is discrete-variable photonic quantum computing, which uses distinct photon states, like polarization, to encode qubits. The second is continuous variable photonic quantum computing, which encodes information in continuous properties of the electromagnetic field, such as amplitude or phase. Researchers are also looking into hybrid approaches that combine both techniques to overcome limitations. In practice, photonic qubits are generated through nonlinear optical processes, such as spontaneous parametric down conversion or for wave mixing, which produce pairs of entangled photons. These photons can then be routed and processed using integrated photonic circuits, enabling complex quantum operations. Applications of photonic qubits are vast. They include quantum communication networks, where photons transmit quantum information securely over long distances. They are also used in quantum computing architectures that aim to create scalable room-temperature quantum processors. Additionally, photonic qubits are beneficial in quantum sensing and metrology due to their coherence and low noise. Overall, photonic qubits representing a promising platform for quantum computing and quantum information technologies. Their robustness, compatibility with existing optical infrastructure, and potential for integration into large-scale quantum systems make them an exciting area of research and development.